Okay, so so here is a video for introducing how to use the Splat Feature Solver. Okay, um, so we are trying to install the Splat Feature Solver here. We start everything from scratch, and we do step-by-step guidance on how to solve all this problem. So the first thing is git clone. I already clone to the right location, and use cd to the split distiller. So this is our repo's name. Although like the paper's name is feature solver, but anyway, we just call it split distiller. And and then if everything goes right, just copy paste this part should work. So here is a what I'm trying to do here. You see, you start from the beginning, you do git clone, and you do cd to the split distiller, and then you clone the environment, create -f environment. So this should be create the environment for you that contains rapid SAI, CUDA toolkit, and some related information. So let's see what's inside the environment YAML. If you have some issue, you can check or install manually. Especially if you are from mainland China, you might encounter a lot of issues like HTTP errors. So first, you see we install from this particular channel NVIDIA label CUDA 12.8. Um, you install CUDA toolkit. The reason why we did not specify the version here and we specify the version here is because we find that if you install CUDA toolkit 12.8, it will install some newer version, not just CUDA toolkit 12.8. But if you first specify the channel and then install, you only install CUDA 12.8. And then rapid SAI. So basically, we want to use CUML. This is a package that we do the HTTP scan or like post aggregation filtering, um, no, post lifting aggregation. Um, we use this package. But usually, you have a precompiled version on Rapid nightly. But if you are mainland Chinese user, you cannot access this source, so you might need to figure it out by your own. But if you are outside China or you have a way to access the Rapids nightly really fast, you can still use this method. And the third thing is that you want to install compilers. So the compilers, this only works if you are on the Linux. So compilers is GCC, or it's not GCC like it. GCC is part of compilers, and it used to cooperate with NVCC, which is NVIDIA C compiler. I don't know, like CUDA compilers and C compilers working together to generate the binary code for you to use to do the feature lifting to make your uh, GPU running. But sometimes your compiler is not at the right version. So usually you might have a 9 point something in your local computer or system-wide computer. You can use Conda to install newer compiler versions in your Conda environment. So the default version would be 13.3 or 14 point something, depends on how the Conda is solving your environment. If you do this on your Linux desktop, or something server, it should solve the problem. And then we go back to here. Go back here. After we used Conda create environment, install the right stuff, and then we go here to do pip install torch 2.7 with the CUDA 12.8. So what this line is trying to do, so it installed 2.7 for torch, but it has a backbone support. If you're using NVIDIA driver, it will support like most of the binary code is previewed or compiled here. So that's what it's trying to do. If you don't add this part, either give you a CPU version or you try to compile locally, you might encounter a lot of problem. And then what you do here is you do pip install dot. So so basically this will open up a setup.py and it write a lot of dependencies you want to install. For example, like py-comap, fused SSIM, and a lot of package. The most four important package you want to install is over here is this is not our package. This is beta splat package. This is gsplat package. So this is two backbone for the Gaussian or splat training pipeline. And segment anything long splat is generate features. Is a special way to generate features. And the gsplat extension is our CUDA backbone for lifting features. So this four stuff is the most important thing you want to install. And after testing, we find it most likely correct. Like it should be installed. Okay, it got some problem. So it got some dependencies error. Bulk of Shapely. I think it's CUML. Anyway, pip list gsplat conda show gsplat. I think it's list or show. Okay, it install gsplat and gsplat extension, segment anything long splat. So most likely this stuff is installed correctly. Okay, so the four sub package installed correctly, although it looks like your installation have some bug, but apparently it's related to NVIDIA CUDA toolkit or CUML. Let's first ignore this part and see what will happen. That's what is interesting. Okay, let's go through the code here. So basically, you want to generate the features. There are a lot of ways you can generate features. You can use SAM-open-clip to generate features, which is very slow. SAM-open-clip is the long split provided backbone for generating SAM features plus clip feature, or it first generates SAM mask, and for each mask it generates clip features and it do some post processing to get final features. It takes usually about 1 or 2 hours to generate those features. So here I don't want to show the progress. I choose to go to another simpler one. Python feature extractor help. Okay, so you can generate source model output device and okay. So source path. Source path. Source path is where your COMAC folder located. So what is a COMAC folder? COMAC folder, you can generate your own things, but you can also download from our, it's not ours, is a lot of people's pre-processing COMAP stuff. So let me show you an example. So you go to data, lerf-ovs. lerf-ovs is the data set we use in the paper. You have figurines is a scene. and you got a bunch of images. This image is the input. You have a folder called input, and you convert it to images. The conversion procedures is a way to undistort your image. This is distorted, and this is undistorted. And undistorted images has a corresponding camera position, which stores in this sparse 0. 0 means the model number, model ID, and you have camera bins, means the camera intrinsic matrix, extrinsic matrix, point 3D. Point 3D means that a key point location in 3D point cloud. And I've already pre-processed this because then we gonna get a points 3D.ply. The only way you can uh, get this stuff is by running the convert stuff or using your CodeMap uh, app by yourself. Okay, so here what we should pass in our program is the source path. Okay, figurines. See the source path, correct? And the model. Here I want to use a mask clip. Mask clip is something really close to SAM open clip, but it's really fast, but the performance is worse or much worse. Mask clip. Is there something else we want to pass? Maybe, maybe not. Let's try this. Okay, it doesn't have a bug here, you see. So it's starting to extracting features. And it should be stored in a particular location called features. Features? Yeah, it will generate your corresponding features here. This is the default location. You can also set your location according to the output directory. Now, if you want to replicate our result, use SAM open clip. Use SAM open clip model. So SAM open clip is SAM plus open clip. It's very slow. I told you it's very slow. Takes 1 or 2 hours. And you also need to specify the SAM checkpoint, like the SAM model 1 checkpoint location. You need to download a CKPT as what we describe over here, and give that location to your to this script, and select the model to SAM open clip. Then you should generate the right features to the feature folder. Or you can specify another folder you want to generate. For example, it's called SAM open clip feature. It will generate to that location. Now, what you need to get is a trained model, trained Gaussian splat. For example, like Gaussian splat, 2D Gaussian, or beta splat. Here we go with the traditional one, the Gaussian splat. But the difference is that we are using another package called gsplat package to train. Um, so probably Python train. So this part is not our contribution. So you can train any other models according to your needs, only if it aligns well with um, the model we have, like the camera model we have. We provide a simple train here. Let's see. No module FAI S S. It does not have this modules. How to solve this problem? Let's go to setup fuse FAISS. FAISS. Where's my cursor? Okay, here. So so you should be have something called FAISS. FAISS. Ah, I know what is going on here. Actually, FAISS is not needed. Mm, the reason why we use it here because Doctor Splat, which is another repo, use FAISS. And why we use that is because we wanted to do a comparison. But actually, if you are a user, there is a way to pass the FAISS. But in case of the robustness, we still install this. So this is the right package you want to install FAISS-GPU. We didn't use that in our package, but Dr. Splatter used, so we also compare with it. So we install the FAISS. Um, Let me check the Gaussian split. Split. Hmm? Okay, there are new bugs out there. How to bypass it? Okay, now we bypass it. Hmm. We train default. Default. I think it's called data dir. Uh, help. 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 CKPT. Data dir. Data factor. Result directory. Okay. Not that hard. Default data dir. Put the COMAP folder directory here and result dir. Just call output in your working directory. Data factor 1. Data factor 1 should means that I use full resolution. And I also add random background color. Random background color. Let's see what's going on here. Okay, it's working. And we can also visualize the training progress. You see, like this is the Gaussian splat. So it should be like trained for several minutes. Usually is around 10 minutes. I think I should have the models. But anyway, um, somehow you have the Gaussian splats. And in our training pipeline, the most important thing is that we modify the camera normalization parameters. So the camera normalization parameter means that you don't want to rescale the coordinates to -1 to 1. We want to train it exactly according to the COMAP position. Why that is important is because during the feature lifting, we still need the same COMAP camera position. So that's the reason why we want to keep exactly COMAP position here. Uh, in fact, the original G-Splat have some settings in the simple trainer that it can change the normalized workspace or no normalized workspace. But here we just hard coded it to use no normalized workspace. Okay, so it takes about 15 minutes to solve the problem. So yeah, now it's like looks much better. But anyway, we just cut here and go back for about 15 minutes. Let me see what is going on here. Uh, Still 1 minute left. So let's see. Yeah. So basically, what you have is something trained like this. Um, you may try another different pipeline. We currently support 2DGS, 3DGS, as well as the uh, the beta, a deformable beta splatting. So these three kernels we support it, and for the performance, if you compare the segmentation result, the best should be 2DGS. Theoretically, it should be 2DGS. Um, but if you want a very good looking pictures, you have a really good image-based matrix, then DBS is the best one. So okay, DBS is famous for its um, reflection, spectral, and how to say like the way to model the lighting environment. But because it's have a really good representation of lighting, it sometimes lose the opacity constraint as what we've put in the 1 plus beta upper bound constraint in the paper. But anyway, it should be well trained. Okay, the thing is well trained here. The features generate over here. See, the features is generated over here, the output is generated over here, and no, CKPT. Okay, so this is a trained model. Then we can do the lifting. How to do the lifting? Python, distillation, help. Help! I also usually forget what's going on here. So dir should be this. Factor, default is one test every. Okay, feature folder. So this all have like default value. Feature folder here. Copy pass. And CKPT here. Copy pass. Um, method 3DGS. So let us see the raw output here. No tick knob, no filtering, no quantize. Let me first explain what. Okay, when it's running, let me explain what is ticked off, what is filter, and what is quantize. So the quantize require mask. You can of course quantize, but you need to do the filtering after quantize. The filtering itself is not like mask filtering, is according to the center of your scene. For example, you only want 20 or 50% of your splats in the center, then you turn these things to the percentage. For example, this filtering is set to 0.5, then you only keep like 50% of your splats in the center. Um, for example, like how we generate a video output. Um, in the website, we do the filtering stuff to check only the internal part on the table, like the toys on the table, as well as the table, not the windows, not the buildings outside. So that is how we do the filtering. But there's no filtering here. We still want to see the output. So this is filter, and the second is quantize. The quantize means that we do the clustering. We do the clustering and give the cluster label. We project it back to the 2D plane compared to the mask. So here we need a mask. If we don't have a mask, we cannot do the so-called filtering, right? Uh, so mask clip or general features don't have the property of doing the quantize. Okay, usually the time taken is around 2 to 3 minutes, but because I'm recording a video is a little bit slower compared to normal one, maybe the memory consumption is is a little bit higher here. And currently I'm all stuck, so maybe my voice is a little bit stuck. But um, anyway, it should be working fine after the feature lifting procedure. So we need to wait about another 4 minutes to see the result. Um, so while doing the feature lifting, I'm also want to introduce more stuff here. So you have this kind of distilling features is mask clip features. You also have another different kind of feature lifting is SAM open clip features. I will show the SAM open clip features later, but because like it takes 1 or 2 hours, but I will directly get the already generated features out there to lift. After the lifting, I will show how to visualize the features using a general viewer. I didn't test on the mask clip though, but it should work fine. Let's just wait a little bit. Okay, yosh, we get things done. Um, then how to check we get things done? So basically we run general viewer help help. Okay, ck ckpt ckpt here, feature ckpt should be here. Copy path and display method 3D GS text encoder should be SAM, not SAM open clip. It's mask clip, right? Mask clip. Okay, let's see. running. Okay. Sometimes like it because you connect the port before and the browser think that you are offending them. Okay, now is working. You see you have like a Gaussian splat here, and then we change to feature. Yeah. So you see like the feature is really bad. That's the reason why we want to do the filtering. Although you can see some feature PCA here, but if you want to see the difference as what we have in the video proposed in the website, you need to do the filtering and then do the feature PCA. Now we should do the query to see if it's working. We first query all the camera query, and we see the attention map. So you see you query out the old camera, and maybe you can also query cube. Okay, you query out the cube. So mask clip is worse compared to the uh, SAM open clip, but generally is working like this. Maybe you can also query out the yellow dot. We didn't use that for the okay, you query out the yellow dot, and you also query something other yellow. So this is Jake, and this is another yellow dot. So basically working, and you can do the segmentation out there. For example, if you want to go, how to say, segment out the old camera, you can do background, table, texture, object. Let's see. Segment. What? Okay, it doesn't work. Maybe, maybe reset. Maybe it's because I typed something wrong. Let's just type table to see. Uh, hmm? Okay, it's working. I don't know why it's just working. So this is how it works. Um, press reset again. Re reset, and we segment out the yellow. Let's try red box. I didn't try to segment out the red box, by the way. Let's first see the attention map. Okay, you can basically just know what is red, but uh, hard to find the good example for mask clip. But anyway, this is how it works. I need to go to have something to eat. When I get back, I can show the SAM open clip stuff. And let's stop here. Alright, we got the features ready. Here you see there's a SAM open clip features, and the format is a little different compared to the normal features. Like normal feature is a dense feature is H times W times uh, C, like the channel you want to have. Usually is 512 for clip feature, but there are like 300 and something for other features. Maybe there are more, like 1,000 features or so. But now what I want to introduce is the SAM open clip features. The SAM open clip features looks like this. You have a file called -f is represent features and -s represent the segments or the masks. So basically it's a multi-level features, h times w times 4, so you have 4 levels, and each pixel at that level represent which mask it corresponds to, and the features is ordered in a sequence of the mask number. For example, like this pixel, it has it has mask 1, it has the mask 6 and mask 7 and mask negative 1. Negative 1 means that this is not valid mask, and 174 can be looked up in the frame 0001 dash F. So this is M by C channel MPY file, and you check what's inside in the 1, 4, and 7 location to retrieve the features out. So basically, that is the data structure, and you can get the SAM OpenClip features from this um, feature extractor using mode SAM OpenClip. But it takes too long, so I directly copy it here. Um, Now to do the distillation, we still run the things Python distill method, but only difference is the features now become another features called SAM OpenClip features. Why we have different kind of um, SAM OpenClip? The different kind of encoding of the features is still running. I think that is because we can, of course, writing different loaders, and yeah, that's how the work is done. And notice that if you have a mask here, if you have a mask here, you can use another flag like quantize and Tikhonov regularizer to get a better result. And for the comparison, I will show you later. Let's first see the non-compared, like non-quantized version from this script. Okay, so the feature has been distilled. Now we need to visualize. Let me check. I think the output is at the right location. The output should be here, right? And the text encoder to be changed to SAM open clip features. And once this is done, the progress. No, no. SAM open clip is not SAM open clip dash feature. It should be just SAM open clip. You see now we still have the same uh, Gaussian splat, 3D Gaussian. But we should have a little bit better features here, and we can do the query. For example, we query the blue elephant. Our keyboard is not working. Uh, Keyboard is not working. Scheiße. Put at the wrong location. Mm. Mm-hmm. Later. Okay. blue elephant query attention map. You see, like this is much better. Like the result is much better compared to the previous one. And you also can query the camera, all the camera. So you can query this one. And you also can query pink ice cream. Yeah, the pink ice cream. So this is much better. And you see, if you query the bag of snacks, okay, with Pikachu on it, because I think like I didn't eat this before, but this should be part of snacks with Pikachu on it. Or you directly query Pikachu should works fine. For example, like if you yeah, like Pikachu is looks really good. Pikachu. Okay, so here you see like this is Pikachu and this is also yellow one. So you can query pretty okay. Sometimes you should like do a little bit slower for the query stuff because if you do it fast, it sometimes give you some errors. But anyway, now it's working fine. And if you want to see the segmentation result, you can also try. But like, let's skip that. Now what I want to introduce is do the quantization. Basically, basically you need to do um, quantize, set to true. No, no. CM open clip feature, CM open clip features, and the quantize set to true. Okay. And this should be take like longer time because we add a quantization here, but like the quantization is itself should be really fast. Um, so let's see what is the final result. All right, so let's see what I need to do here. So we just finished the mask quantization and filtering. Take about 10 minutes. So if you already have like lift feature, you can modify the code so that it can run the quantization. But but basically you just get something like this refined features. Um, and what's the difference between the quantized feature and not quantized feature? There are two major differences. The first difference is we do the quantization, so make like each cluster of features one cluster. And the second thing we're trying to do is to do the filtering. The filtering means that if we have a feature, we project on the 2D mask and filter out those masks that is unreliable. Mm, so here, to use that, I think, yeah, I think just doing this, you can use the quantized features. The quantized features has a major difference compared to compared to other features like the normal features. If you change this to feature, you can see a little bit difference, but not much. But if you do the query, you can see a lot of difference. For example, like bag of of let's directly do Pikachu. Is this Pikachu? Okay, and change this to attention map. So you see, it becomes a something like this. Things become very quantized. Bag of snacks with Pikachu. If you do the query like this, it will directly give out the red part. It's whole red. Like it's not like the front is red, the back is not red. It's like full of red. And and for the Jake the dog, it should be the same. You see, like a whole unified red. So for the segmentation, this is much better. For example, the background, texture, object, table, toys. I don't think toy is a good choice. So when we do the segmentation, yeah, you see like he's already segmented these things out. Maybe there is a doc. Let's change the RGB. Okay, so if you want to segment this doc out, you just put the negative query here, yellow doc segment. Yeah, this is the right uh, Jake the dog you want to segment out. It looks pretty okay, I think. So that's how it works, and is much better compared to the older version. And you can do 3D segmentation out there. And if you want to export these splats, I think you can go find some part in the code. Actually, actually, I can tell you how to export. So here is the in the extension we have some module gsplat extension, and utility. There's a viewer, and here you see when we have segmentation, yeah, we generate a mask, and this mask can be used to segment things out. Um, you just directly after self splats add an additional function here called self splat dot save something. Then it should work. But I'm not doing an app here, so this is what I want to show. Mm, So the next step would be introduction of a function called filter. So although in the quantization we have a filtering, but it's not like full filter. So that to get exactly the same as our video output, there is another function called filtering. So filter set to 0.2, and let's see. So the filter is kind of according to the center of the camera due to filtering, and quantization means that we filter the unreliable mask. So so they're two different things. Yeah. And after this is accomplished, I will show the result again. So yeah, almost accomplished. But before accomplish, I have several notice and several um, how to say like several words. Somebody might need to know. So the quantization part, um, and the lifting part can be largely shrink if you preset the filtering. The reason why the filtering is relatively slow is because I didn't set filtering at the beginning. Um, for fair comparison is usually made for the benchmark. So let me show the code here. I think it's somewhere here, right? So in the distill, there's a runner and there's set dataset, set splats, and start to do the distillation. So you can first do the filtering of the geometry, like you select a part of this Gaussian splats you want to lift the features, and then start to lift the feature, and then do the quantization, and then just give out the result. This is the first way of doing so. The second way is that you lift the features, and you do the quantization, and then you do the filtering. Okay, so there are two steps, like there are two sequences you can do this stuff. The reason why we choose to select the second one is not because that is better or like that is the best for industry. It's because we want to do the fair comparison. Because if you do the filtering first, then you need to select a threshold like point 0.2 or point something, point 0.2, point 0.3 for you to do the threshold selection. You need to first check out the environment and to see if point 0.2 or point 0.3 is including your environment or not, which introduced the manual intervention. But from my colleague, they really like the filtering first because it's fast and they actually only need the table, not the, for example, in the figurines scene I just showed around, the only thing people focus is actually the table, is not the wall, the the glass, the buildings around here, the hallway. So they want to do the filtering first, focus on the table, and then start to do the feature lifting part. Um, so our published version should not do that part for benchmarking. But if you want to modify it for your own use, you can just directly put this part, like distill args filter, before distillation, before this for loop, then it's much faster. Okay, so that is the few notes I want to mention here. And yeah, we're just waiting for the accomplish of the job. Okay, I think like um it's working. So when you have a filtering features, what you need to do is to select the checkpoint you filter out. So a little bit complicated. Go here, you check there's a features, filtered refined feature. So if you do the quantization, the name of the feature is refined. If you do the filtering, is filtered. So if you do the filtering and the quantization is called filtered refined features. So this is the right features, and there also should be a correspondent um, checkpoint. So it's a filtered PT. So you have CKPT filter, filter PT, and here is a filtered refined. Yep. And then things should work. Let's wait. No future found? Okay. I think I Use the wrong feature. Filtered refine features. Filtered refined. I don't know. I think this is the right one. Okay, this is the right one. Uh-huh. Sometimes if you connect it too frequently, your Chrome or your Explorer reject the the access. Ah. Oh. So basically, you select the filtering, and it gives something like this. So you can actually change the filtering number here to lower. So I think I select point 0.2 right here. You can change it to point 0.1 or something to get a better result. But anyway, so this is what we got. And so you see here, you see a much better PCA result. And if you want to do the attention query, for example, like yellow duck, yellow rubber duck query, then we'll give this, right? So that's basically all our um repos function. But it also support other like 2DGS data DBS model. You just change the corresponding method here. Should be fine. Okay. So the whole logic is that you need to first train the primitives and then lift features to the primitives using several attributes and then to visualize. And when you train, you need to select the right model you want to use. When you lift, you also need to select the right method you want to use. And when you visualize, you need to also select the kernel you want to use. And you can lift different features. Um, yeah, that's all.